Okay, so let us start the sections now. So today we're going to look at chapter 6. Chapter 6 is a circular motions, and then how are we going to solve the questions in chapter 6? Actually, it's very, very similar to chapter 4. Okay, we are going to apply Newton's second law in solving the questions here. So let us begin with 6.1. So 6.1, uniform circular motions. We're going to describe what is a uniform circular motion. Now, when we talk about uniform circular motions, there are two things that we need to take notes. The first one is what happens to its magnitude. And then the second one is the direction. So first thing, if an object is moving in a circular motions, uniform circular motions, then we say it is moving at constant speed. Okay, so the speed remain constant. So for example, if initially object is moving with, okay, V initial is 10 meter per second, then V final is also 10 meter per second. But take notes, even though it's still using the symbol V, but now this V represents speed, not velocity. So you have to be extra careful with the terms that you're using. So the magnitude of velocity, okay, if you look at the notes, it says the magnitude. Okay, the magnitude of velocity remain constant. So the magnitudes of velocity, actually it represents speed. Okay, magnitudes of velocity, it represents speed. So speed remain constant. So the value tends to remain constant. But then the direction, it continuously changes as the object moves around the circle. So if you look at the diagram, V1, the direction is going to the right, but when it moves to V2, the direction is southwest. Okay, it's pointing towards southwest. So the directions of V, it keeps changing. So how to determine the directions? Again, we are looking at the tangent of the circle. So for example, now let's say this is your object, positions number 3. So how to determine the directions at positions number 3? You draw the line that is joining this point, the position number 3 and the center of the circle. Okay, and then the line that is perpendicular to this radius, that is the directions. Okay, so in this case, I have a direction that is going to towards here. Okay, going up. So this is 90 degrees. So perpendicular to the radius. That is how we determine the directions of the velocity. So you look at the line, the positions, and then you draw a line that is joining the positions that you want to the center of the circle, and then you make another line that is perpendicular to the radius. That it represents the directions of the velocity of the object. Okay, so the magnitude of the velocity, which is the speed, remain constant, but then the directions continuously changes. That is uniform circular motion. So if the questions ask you to identify which situations given is uniform circular motions, which object is moving with uniform circular motions, then you try to look for the keywords. Constant speed and direction continuously changes. Okay, so acceleration is defined as the rate change of velocity. In case of a circular motion, because our velocity is not constant, okay, because the direction it keeps changing, therefore the acceleration is not equal to 0. Okay, so let's look at this thing. When we say velocity is constant, okay, velocity is constant, then what does it mean? It means A equals to 0. But now what we are looking at, we say speed is constant, but not velocity. Speed is constant, it doesn't mean that A is equal to 0. A could be not equal to 0 if, okay, if directions changes. Okay, if directions is changing. So directions changing, A is not equal to 0. So can you see the difference? So if you are talking about velocity constant, then A 0. If you are talking about speed, then A is not 0 if the direction is changing. And in this case, in our circular motions, speed is constant, but the definitions, according to the definitions of uniform circular motion, it tells you the directions keep changing. Therefore, in this case, we have a non-zero A. Okay, we have a non-zero A. So therefore, an object in a circular motion is continuously accelerating. So it has a non-zero A. Okay, so even when the speed remain constant. So make sure you know the difference between velocity constant and speed constant, right? So even though both of them, they have same value, but because of the directions, so the A could be different. All right, A could be different. So another important case that of an object moving in a circle, such as we have a bar at the end. So this is the examples. Okay, we have examples here, and we are going to go through them after we finish with all the definition. So a bar at the end of a string revolving around one head, and then the circular motions of moons about the earth. This one we are going to look at it in chapter 7. Okay, chapter 7. And then a car traveling around a turn, and parts of the motions of a roller coaster. So all these, they are examples of circular motion. All right, and we are going to look at them later today. All right, so these are the important terms in the circular motions. Okay, we need to know all these terms, including how to calculate it. So the first terms is angular displacement. Okay, the terms is missing, so make sure you add it in your notes. So angular displacement, which is a theta. Okay, the symbol is theta. So to describe circular motions, we use angles instead of distance. So the relationship between circular arcs, which is the curve, this curve, okay, this is what we call circular arc, our S, and the angular displacement theta is given by S equals to R theta, where R represents the radius of the circle, okay, radius of the circles. So angles is measures in radian. So what are we going to calculate in this chapter? The terms that is very important in this chapter is revolutions. So one revolutions, which is one cycle, equals to 360 degree, okay, which is equals to 2 pi radian, right? 2 pi radian. So you need to know how to convert from revolutions to degree to radian, right? So one revolution is equals to 2 pi radian. 360 degree is equals to 2 pi radian. So you need to know how to convert the unit. Okay, in this chapter, we are going to use a radian quite often. So make sure you know how to do the unit conversions, especially when it involves revolution. So the second things, okay, just now we were looking at the angles, okay, the displacement in a circular motions. We call it angular displacement. Now we are going to look at the velocity in a circular motion, in which we call angular velocity. Okay, angular velocity. So angular velocity is equals to the displacements over time. So basically the equation is same as the equations in the linear motion. In linear motions, we have V equals to delta S over delta T. When it comes to circular motions or rotational motion, okay, we use angular velocity omega, which is equals to delta displacement, okay, angular displacement divided by del T, the changes in a angular displacement divided by the changes in the time, right? So unit is radian per second. So basically the equations in the linear motions and also in circular motions, they are very similar. All right, they use the same equations, but with different symbol, different variables. So period is the time taken to complete one revolution. So make sure you know what is the difference between a normal times and period. Period is time taken to complete one revolutions, and we use capital letter T. So if the times given is not for one revolutions, then you use small letter T. Okay, small letter T for not one revolution, capital letter T for one revolution. Okay, so make sure you know the difference between times and period. Times, it could be the time for one revolutions or not one revolution, but the period is definitely for one revolutions. So since omega is equals to theta over time, so now you're looking at one revolution, which is equals to 2 pi. Therefore, we use 2 pi divided by capital letter T. Okay, 2 pi divided by capital letter T, because you're looking at the revolution. So 2 pi represent one revolution, and then capital letter T, time taken, okay, time taken to complete one revolution. Okay, so to rearrange the equations, you have period is equals to 2 pi over omega. Okay, period is equals to 2 pi over omega. And then frequency. Frequency is number of revolutions per second. Okay, so F is equals to 1 over time. So just now you look at how long does it take to complete one revolution. Now you see if you're given time 1 second, okay, then you can do how many revolutions in that 1 second. So if you have a 50 hertz, that means that you can do 50 revolution in 1 second. Okay, 10 hertz, 10 revolutions per second. So the unit for frequency, okay, the unit for frequency is either hertz or as -1. So you have two different units for frequency. So the main difference between period and frequency, period is how long does it take to complete one revolution. Frequency is how many revolutions can be made in 1 second. So just now we were looking at the angular velocity. Okay, now we have a tangential velocity, which is linear velocity. So it has two different names. Okay, one name is known as a linear, or most often we call it tangentials. Okay, because we take the tangent of the circle. So it is directed tangentially to the circular path and always perpendicular to the radius. So this is what we call tangent to the circle. Okay, always perpendicular to the radius of the circular path. So the magnitude of linear velocity of an object in circular motion is constant, but then the direction continuously changing. Okay, so that is the definitions that we have seen just now. And now we are going to look at the relationship between linear velocity and angular velocity. So just now we have an angular displacement S equals to r theta. So a substitute, okay, divided by time, because now you want to change them into velocity. So from displacement into velocity, you divide it by t. Therefore, we have V equals to r omega. Okay, V equals to r omega. So that is the relationship between angular and linear. All right, so linear is equals to r times angular. Okay, linear is equals to r times angular. Okay, so now let's try to do some unit conversions. Okay, let's try to do some unit conversions. So we are going to convert units between degree, radians, and also revolutions. So revolutions, sometimes they call it a rotation, sometimes they call it cycle. Okay, so you have a 0 degree. 0 degree is equals to 0 radian, which is equals to 0. Okay, now you change it into decimal. So this one is in terms of pi. Okay, this one is in terms of a decimal. So 90 degree is pi over 2 radian. How do I know 90 degree is pi over 2 radian? Now, it's very simple, okay? So 90 degree divided by 360 degree. And then times with what? Times with 2 pi. Then you can get the value for, you can get the radian for 90 degree. Okay, you can get the radian for 90 degree. So how to do this? Okay, now let's begin with mathematics. Okay, let me erase it first. Okay, so we want to know 90 degree equals to how many radian? Okay, so we put a question mark here. But what we do know is 360 degree equals to 2 pi radian. So when we have two relationships like this, okay, this concept actually can be applied in any chapters, in any subject. So when you manage to form two equations like this, what are you going to do? You're just going to use equations 1 divided by equations 2. Okay, so you use 1 divided by 2. So you obtain a relationship. 90 degree over 360 degree is equals to, now this question mark, I'm going to call it x. So x over 2 pi. So from here, you can determine the radian. So x is equals to 90 degree over 360 degree. You move 2 pi to the other side of the equation, so times 2 pi. So from here, you can determine the radian in terms of, the 90 degree in terms of radian, which is pi over 2 radian. All right, so this is how you solve it. So the most important thing is you know how to form these two equations. Okay, and this concept, this idea, this technique, this method can be applied in any subtopic. Okay, if the questions ask you to do unit conversion, if the question asks you to find some unknown, and then you are given another set of known value. So equations 2 is another set of known value between two different quantity. One is degree, one is radian. And then equations 1 is 1 in degree, 1 in radian, but the radian is unknown. So you can use this relationship. Same things, if you're given radian, okay, for example, now let's look at the pi radian. Pi radian equals to how many degree? Okay, let us try how to do unit conversion. Okay, so again, let us begin with, okay, now we know 360 degree is equals to 2 pi radian. Now we want to find out pi radian equals to how many degree. So again, we have two set of equation. Okay, two set of equations. So what are we going to do? We use equations 1 divided by equations 2. So again, we have x over 360 degree equals to pi over 2 pi. Rearrange the equations, you're going to get x equals to 180 degree. So this is how you do unit conversion. Okay, convert from radian to degree, from degree to radian. Okay, and same things, you can do it for revolutions. Okay, you can do it for revolution. So for example, let's see. Now, I have pi over 2 radian. Okay, pi over 2 radian equals to how many revolution? Let us repeat the same thing. Okay, let us repeat the same thing. So now we want to find out pi over 2 radian equals to how many revolution? What we do know is 2 pi radian equals to 1 revolution. Okay, this is the information that we have. So now we have formed two relationships, one with unknown, one without unknown. Okay, then what are we going to do? We use 1 divided by 2 as usual. So 1 divided by 2, we have a pi over 2 radian divided by 2 pi, and then equals to what? Equals to x over 1. Okay, equals to x over 1. So we rearrange the equations, we will find that x is equal to 1 over 4 revolution, okay, which is 0.25 revolution. So this is how we do unit conversions between a revolution, degree, and also radian. All right, the most important thing is you need two equations first. One with a known relationship, one with unknown value. So that is how we solve it. All right. So quite often, questions will ask you to give a final answer in revolution. So make sure you know how to convert from radian to revolution. So a 270 degree is 3 pi over 2 radian, or in terms of decimal is 4.17 radian. And then 360 degree is 2 pi radian, or 6.28 radian. Okay, 6.28 radian. So now convert 3 radians to degree. How are we going to convert 3 radians to degree? So 3 radian equals to how many degree? Okay, so you form an equation first. So now I'm going to call it x. Okay, equals to x degree. And then what I do know is 2 pi radian equals to 360 degree. So I'm going to call it 1, I'm going to call it 2. So let's use 1 divided by 2. So 3 over 2 pi is equals to x over 360. Okay, so you rearrange the equations, eventually you are going to get, okay, x is approximately equals to 171.9 degree. Okay, 171.9 degree. So this is how you do unit conversions. So how about 3 degrees to radian? Basically, you do the same thing. So now you have an x radian equals to 3 degree. 2 pi radian is equals to 360 degree. Okay, so again, equations 1, equations 2. I'm going to repeat the same thing by using 1 divided by 2. So now what I have is x over 2 pi radian equals to 3 degree divided by 360 degree. So rearrange the equations, I will have a x which is approximately equals to 0.05 radian. Right, 0.05 radian. So this is how we do unit conversions. So make sure you take notes, because unit conversion is very important in this chapter. Okay, it's very important in this chapter. Oops. Okay, so this table, I will leave it to you. All right, you tried it by yourself. So I will give you an answer in our next lesson. Okay, next sections, I will show you the answer. But this one, I want you to try it. Okay, try it yourself. So make sure you complete it. Next class, I will give you the answer. Okay, we are done with the 6.1. 6.1 basically is the unit conversions and also the definitions. So now we're going to focus on the 6.2. Okay, oh yeah, before that, I think there are some things missing in your notes. Okay, so what I want you to do, I want you to add something into your notes. Okay, now these two things. 1 revolutions per second. Okay, 1 RPS and 1 revolutions per minute. So I want you to know these are 2 units. All right, it comes out very often in your questions. RPS and RPM. So what does it mean by RPS? RPS stands for revolution per second, which is 1 revolutions divided by 1 second. Okay, now if you look at the unit, it is 2 pi radian per second, which tells you this is your angular velocity. Okay, angular velocity. So this thing is missing in your notes. I want you to add it in your notes. So another unit conversion is what we call revolutions per minute, RPM. So quite often the question will just tells you now you have an object that is moving with 10 RPM. Then you have to know what does it mean by RPM. So RPM is 1 revolutions per minute, in which it means 1 revolutions over 60 seconds. Okay, which is equals to 2 pi radian over 60 seconds. Then if you calculate it, you're going to get 0.1 radian per second. So again, the unit itself, radian per second, it tells you this is angular velocity. Okay, this is angular velocity. So this thing is missing in your notes. I give you 1 minute to write it down. Okay, this 2 is very, very important. Okay, it comes out very, very, very often in your questions. RPS and also RPM. So 1 minute for you to write it down. Okay, so far I hope you're clear on unit conversions. You know how to do unit conversion. Okay, because of this chapter, the only difficult part is the unit conversions. The rest, it's very similar to chapter 4. Okay. So let us continue. Okay, so next we're going to look at centripetal force. So we are going to go back to force again. So centripetal force, the first thing, okay, before we look at force, we must know the acceleration. Okay, because the force is F equals to ma. So in order to calculate force, you need accelerations. And because you're looking at centripetal force, therefore you need centripetal acceleration. So centripetal accelerations has another name, is called radial acceleration. Okay, so don't panic if question asks you to calculate radial acceleration, because it represents centripetal acceleration. Accelerations of an object moving in circular path whose direction is towards the center of the circular path and whose magnitude is equal to the square of a speed divided by the radius. So AC, okay, A with a subscript C represent centripetal acceleration, is equals to V squared over R. Okay, and it is equals to r omega squared. Okay, why r omega squared? Because v is equals to r omega. So remember, okay, so you sub v equals to r omega into the equations, and then you obtain AC is equals to r omega squared. So you have two equations for AC, centripetal acceleration. So the direction is always pointing towards the circle. So if you look at the diagram, okay, the diagram, the arrow of AC, it's always pointing towards center. Okay, and if you look at the term centripetal acceleration, centripetal itself means center seeking. Means it's always looking for center of the circle. All right, and it is perpendicular to the linear velocity. Okay, it is perpendicular to the linear velocity. All right, so next. So this is just the definitions, okay? You just have to know the definitions for your UPS. So calculations, what do you have to know? You just have to know the equation. All right, so 6.2, we are going to focus more on how to form equations. I will go through the definitions quickly. So according to Newton's second law, when an object is accelerating, then it must have a net force acting on it. Therefore, an object moving in a circle, it must have a force applied to it to keep it moving in a circle. And this force, okay, will give it a centripetal acceleration. So Newton's second law can be applied to a circular motion, since we know summations F equals to ma. And since now you are looking at the centripetal force, okay, so we rewrite summations F, this whole thing, into Fc. Okay, Fc. Okay, so Fc is equals to MAC, and since AC is equals to V square over R, so MV square over R, and also AC is equals to R omega square, so we have MR omega square. Okay, MR omega square. Now, if you look at this relationship, there's something very important in which it tells you Fc is actually net force. Okay, it's actually a net force. Net force acting on the object to keep it moving in a circular motion. It doesn't represent any basic type of force, which means you shouldn't put Fc in your free body diagram. Okay, dia bukan force apa-apa, dia bukan an individual force such as your tensions, your normal force, the weight. No, okay? So it is just a total force. It represents total force, it represents net force. So you don't include it in your free body diagram, okay? Fc shouldn't exist in free body diagram because it is net force. It represents total force, summations force, okay? So Fc represents summation force. It is not any other types of force. It is not a basic force, okay? It just tells you the total force to keep your object moving in circular motion. That is our centripetal force, Fc. So centripetal force is defined as a force required to maintain a body in a circular motion. That is what I told you just now. So Fc, it represents the net force, the total force that is needed to keep objects moving in circular motion. Okay, it doesn't represent any basic forces. So remember, don't put it in your free body diagram. Okay, do not put Fc in free body diagram. Right? This is a very common sin mistake in the exam, where students treat Fc as one of the basic force, which is wrong. Fc actually, it represents net force. It represents summations F. Just that in chapter 4, we call it summations F. In chapter 6, we call it Fc. Okay, but they both mean the same thing, which is total force. So the centripetal force is not a new kind of force. The terms merely describe the directions of the net force is directed towards the center. Okay, so the reasons why we have this C as a subscript, because it tells you that Fc also pointing towards the center, same as your AC. Okay, so directions of Fc and AC, Fc and AC, they are always the same. Okay, they have the same direction, which is always pointing towards the center. So in which it means if you have an object, for example, this is the center, okay, and then you tie strings and then you swing it in the vertical circle. So the force, the accelerations is always pointing towards the center, regardless of where is your object. So let's say now your object is at positions 1, So both AC and FC, they are pointing towards the center. If your object is located at here, okay, now let's assume this is your position number 2. Same things happen. AC towards center, FC towards center. So in which it tells you the directions of your AC and FC, they are always changing. Okay, they are always changing. So as your objects rotate, the directions of AC and FC, it keeps changing, right? So it's unlike your V, okay, velocity is perpendicular to them. Okay, your linear velocity, V, is always perpendicular to them. Okay, your V is always perpendicular, but then AC is always pointing towards the center. So that is the difference between AC, FC, and also V, okay, between these three terms. Okay, so these are some of the examples. So the first thing, the centripetal force, is it has it when car is moving in a circular path. Okay, when car is moving in a circular path, FC is always pointing towards the center. So this is your FC. So frictional force between tire and also the road, okay, give you FC. It is the force that keeps your object to move in a circular motion. Okay, so frictional force between the ground and the wheel is the force that keeps your car moving in circular path. So in this case, we let FC pointing towards the center. Okay, we'll go through the equations one by one after this. And then the second thing, swinging a ball at the ends of a string. So if you swing a ball, so this one, okay, the centripetal force is always pointing towards the center. So let's assume you are the center. Okay, so centripetal force is pointing towards you. So the centripetal force in this case, the force that is keeping this ball to move in a circular motion is the tension. Okay, the string. So tension keeps the ball to move in a circular motion. And next one, now you have a sun and then you have an earth. Okay, so the earth always moves in a circular motions because of what? Because of the gravitational force. Okay, because of the gravity of the sun. So we'll look at this in the next chapter, chapter 7. And then the D, okay, D, now you have a roller coaster. So this car can move in a circle. Why? Now this car, if you look at the car is in contact with the track. So in this case, what it has? It has a normal force. And at the same time, actually it has weight as well. So weight and normal force, they are the force that keeps this car to move in a circular motion. Okay, the car will move in a circular motion. So not just normal force, okay, but you have two types of force in this diagram. Okay, two types of force. And then the last one, okay, now you have an aeroplane, okay, the airplane. The airplane can move in a circular motions because of what? Because of a force that we call lifting force. Okay, so we don't have a lifting force in our syllabus except when it involves an airplane. So the lifting force acts normally to the airplane body. When the aeroplane tilts, the horizontal component acts normally to the plane towards the center of the circle. So basically, this is your lift force. Okay, this one. Right, this one is a lift force. So this example, we call it conical pendulum. So we have 3 examples here. So this means that the horizontal component of the lifting force, okay, is acting as a centripetal force. So this is a lift force. So when your object rotates, centripetal force actually is pointing towards the center. So this is your FC. Okay, this is your lift force. Lift force, we call it what? Yeah, we call it FL if I'm not mistaken. So the X component, the horizontal components of lift force is your circular motion. Okay, it's a circular motion. So we'll go through it one by one. Okay, the examples. So this one is not in your notes. Okay, this one is not in your notes. So yeah, let me see. This is an additional notes. It is not in your tutorial notes. Okay, this is extra. So what am I going to do? Yeah, I will give you these notes in your group. Okay, in your groups, what you are going to do now, you just write down the answer. Okay, or you can also copy it down if you want. Kamu boleh salin, okay, atau kamu boleh tulis jawapan, and then soalan salin nanti. So saya akan bagi kamu handout. Okay, saya akan bagi kamu handout tanpa jawapan. Okay, let me find the notes. Okay. All right, questions. I put it in a Telegram groups already. So what are you going to do now? You're just going to look at the screen and see how are we going to draw free body diagram, and how are we going to determine the directions of a circular motion. Okay, circular motions. Right. So before we look at the handout, okay, let me go through a few simple example with you first. Okay, because the handout, the example is a slightly more complicated. So again, this one is not in your handout. Okay, this one is not in your handout. You just pay attention and see how are we going to determine the, how are we going to form the equations. So let's look at the first diagram. Okay, uniform circular motions, we have three different cases. First one is when we are looking at horizontal circular motion. Horizontal circular motion means that your centripetal force is happening along x-axis. So let's look at the first case. Now you have a hand. This hand is swinging, okay, swinging a ball in a horizontal circular path. So what we have now, we have an object here. Okay, we have an object. So let's do a free body diagram for this object. So this is my object. Okay, this is the ball. So I transfer the ball to a dot. So ball come with weight. Okay, so it has a W. And if you look at the diagram, let's assume my ball is on the left-hand side now. So the ball is on the left-hand side and my hand is at the center. So hand is acting as a center of the circle. Okay, center of the circle. So in this case, okay, I have a tension that is pointing towards the center. All right, this Ft actually is a tension. I change the symbol to T. So tension is pointing toward the center. So what are we going to do now? Okay, now that I have this diagram, first things what I want you to do, you state the directions of AC first. So if your tension is going towards the center, okay, and then your AC is also pointing towards the center. That is what we do know. Now your object is on the left-hand side. So AC is definitely going towards the center. Okay, look at the original diagram. T going towards the center, AC going towards the center. So now that I have this diagram, what am I going to do? I'm going to apply Newton's second law. So Newton's second law tells me that FC equals to MAC. Okay, so same as chapter 4, we keep MAC, we don't do anything on the right-hand side of the equation. Now let's see FC. What is the force that we have, okay, that keeps our object to move in a circular motion? In this example, the force that is keeping my object to move in a circular motion is just tension. Okay, weight has nothing to do with the circular motion. Therefore, you just put T in the diagram, T in the equation, sorry. Okay, you just put T in the equation. So the final equations that can be used to represent this diagram to solve this question is T equals to MAC. Okay, so T is the force that keeps my ball to move in a circular motion, to rotate in a circular motion. Right? So let's look at the second example. Second examples of a horizontal motion is the motions of a car around a roundabout. Okay, around a flat curve. So let's assume, okay, now what I'm going to do, I'm going to draw a free body diagram for the car. Okay, let's assume I'm watching the object from here. Okay, I'm watching the object from the back of the car. So if I watch the car from the back, okay, let's assume, okay, I'm standing right here. So I watch the car from the back. So what is the things I'm going to see? So this is my object, which is car. Car is an object. Every object comes with weight. That is what we know. Car is moving on its surface. Therefore, it has a normal force. Okay, it has a normal force. Now, if I'm standing right here behind the cars, the center of the circle is on my right-hand side. Right? And the reasons why my car can move in a circular motion is because of this frictional force. And frictional force is pointing towards the center. Okay, so this is me. Okay, this is me. So if I watch it from the back, the frictional force is going to the right. So what do I have now? I have an F going to the right-hand side, which is the frictional force. And what is the directions of AC? Now again, you have object moving in a circular motion. Therefore, AC is also pointing towards the center. So I'm going to add AC outside my free body diagram, right? So what are we going to do now? Now that I have a complete free body diagram, I'm going to apply Newton's second law again. So FC equals to MAC. Okay, this is the second law. So MAC, I'm going to keep it. I'm not going to do anything about it. And then what am I going to do? I'm trying to find out what is the force that keeps my cars to move in a circular motion. So according to my free body diagram, the force that is acting towards the directions of AC that has the same directions as AC is a frictional force. Therefore, I know frictional force is the only force that keeps my object to move in a circular motion. Therefore, it's frictional force equals to MAC. So this is the equation for this question. Then how about N and W? Now N and W, because my car, it doesn't move up and down. It just moves along the X component, right? Therefore, for N and W, we can say summations Fy equals to 0. So we go back to chapter 4. So N minus W equals to 0 and N equals to W. So that is how you solve it. All right. The only difference is now that our X component, okay, summations Fx equals to Ma. Okay, the X component have acceleration. But we don't write summations Fx. Why? Because now X component, we have circular motion. Okay, we have centripetal force. Therefore, what we are doing, we just change summations Fx into Fc. Okay, actually it's the same. Idea is just exactly same as the chapter 4. Okay, idea dia sama seperti chapter 4 kamu buat X component, kamu buat Y component. Yang beza, kamu tengok circular motions berlaku di komponen mana satu. Berlaku di X ke, berlaku di Y. So from there, you expand the equation. So if it happens along the Y component, then your summations Fy is equals to Ma. Then summations Fy is your Fc. So Fc equals to Mac for vertical component. Same thing. Okay, same thing. So this is for horizontal circular motion. So next, we're going to look at the second examples that we have is vertical circular motion. Okay, so vertical circular motions, the things that we have to take notes. Okay, we often look at two different positions, at the top and at the bottom of the object. Okay, so let's look at this diagram again. So now you have a ball. So what happens at the top? So when the object is at the top, okay, you have a tensions pointing downwards because now you have a string. The string is holding the ball. So when it is at the top, this is my free body diagram, the object. I have a tension that is being tied to the objects. Therefore, I have a tension that is going downwards. Ball is an object. Like I told you before, every object it comes with weight. So it has also W. Okay, it has W as well. So when object is at the top, what is the directions of AC? Remember, AC always pointing towards center. So when the object is at the top, AC is going down. Okay, AC is going down. Now, why is it important to determine the directions of AC? Because directions of AC tells you the directions of the positive vector. So in this case, downward is positive, upward is negative. So when you expand the equations, how are you going to expand it? Okay, Fc equals to MAC. Okay, so MAC, you can keep writing it down as usual. Then how about FC? So same thing. So you look at what is the force that causes my object to rotate. According to free body diagram, I have two forces that is pointing towards the same directions as AC, which is tension and also weight. And both of them, they're pointing towards same direction. Therefore, T plus W equals to MAC. Okay, T plus W equals to MAC. So that is for the object at the top. Now, how about the object at the bottom? So for object at the bottom, okay, so this is my free body diagram. So the object, when it is at the bottom, well, every object comes with weight and weight always pointing downwards, right? And then the strings is being tied to the object. And now my tension is pointing upwards, okay, because now my string is above the ball. So upwards T, but downwards W. How about the directions of A? Remember, AC always pointing towards center. So now, when my object is at the bottoms of the vertical circular motion, my AC is pointing upwards. Okay, AC is pointing upwards. So from here, we can then determine the directions. Okay, so upward is a positive direction, downward is a negative directions now. So again, repeat the same thing. FC equals to MAC. So FC, what do we have? So upward is positive, therefore T minus W equals to MAC. Done. That is the equations for when object is at the bottoms of the vertical circular motion. Okay, so when it comes to vertical circular motions, you have to take into considerations the weight of the object. All right, so if your object is moving in a horizontal circular motions, weight is not that important. But when it comes to vertical circular motions, you have to take notes. Okay, you have to take notes. So this is how you form equations. Okay, now think how to determine the minimum speed needed to keep the ball swinging in the vertical circle. Okay, so what is the things that we need to know? Okay, what is the speed that needed to keep the object to move in the vertical circle? So what happens here is if the object is moving in a vertical circular motion, this string will experience tension. Okay, string will experience tension if object is moving in a circular motion. All right, so this case, usually it will ask you, what is the minimum speed to keep the object swinging in a vertical circle? Then you have to look at the top. Okay, so if the object, it doesn't have enough speed to move in a vertical circular motion, what is going to happen? Oops. What is going to happen? So this is your center. The string will become like this. Okay, the object will drop because it has no, the speed is not fast enough to keep it moving in a circular motion. So usually when this question asks you to determine the minimum speed, you look at what happens at the top. Okay, at the top of the object. So if it doesn't have enough speed to keep it moving in a circular motion, then it will become a loose. So when it becomes loose, what happened? We assume T equals to 0. So from here, you can then determine the minimum speed. So when object is at the top, we have a T plus W equals to mg just now, equals to MAC, sorry. Okay, so if T is equals to 0, then W equals to MAC, which is equals to MV squared over R. So from here, you rearrange, you can then get the value for V minimum. Okay, V minimum equals to 1. So this is how you determine the minimum speed. Okay, determine the minimum speed for the objects to keep rotating in a vertical circular motion. All right. So if it doesn't have enough speed, then when it reaches the top of the circle, it will become a loose. So when it is not a straight string, okay, when it drops, then we assume tension equals to 0. Okay, we assume tension equals to 0. So if tension equals to 0, W straight away equals to MAC. So from there, you can then determine the minimum speed. So if you have a speed that is less than this minimum speed, then you will no longer have a vertical circular motion. The object will drops. Okay, the object will drops. So same thing happens, okay, if a object, the string breaks. Okay, if a string breaks, then the T will also equal to 0. So example 2, same things happen. Now you are sitting inside a Ferris wheel. Okay, so you calculate the circular motions that happens in you. So you are sitting in a Ferris wheel, you have a normal force that is going up, your weight is going down, but at the top, AC is going down. Okay, therefore you have equations W minus N equals to MAC. So this is one at the bottom. So when it is at the bottom, what happens now is N minus W. So now you can see the difference in the equation. At the top and at the bottom, you have different equations. Why? Because of the directions of AC. Okay, because of the directions of AC. Okay, now let's see. Okay, the equations, I will leave it to you. Okay, you explore it by yourself. Now let's think. Which positions would give you smaller readings on the weighting scale? So let's say now you want to write, you are taking a weighting scale into a Ferris wheel. All right? And you try to make yourself feel better. Okay, mungkin sekarang weight kamu dah tambah. Okay, but then you try to make yourself feeling better by bringing a weighting scales into a Ferris wheel, and then you want to measure it at a certain position because it will give you a smaller reading. So which positions will give you a smaller reading in your opinion? Which positions will give you a smaller reading? So if you look at the equations, now you have N, okay, and then and W. N and W which variable give you readings on the weighting scale? This is the part that students always got it wrong. W is a fixed value, if you remember. Why? Because W equals to mg. It is fixed. So it won't change. Okay, it won't change, which means the readings on weighting scale is actually your normal force. Okay, it's actually your normal force. So you just rearrange these two equations and see which one give you a smaller n. So if you're at the top, n is equals to what? N is equals to mg minus mv squared over r. If you're at the top, n is equals to mg plus mv squared over r, which means if you're at the top of the Ferris wheel, you will have a smaller readings on the weighting scale because n is equal to your actual weight minus the centripetal force. But if you're at the bottoms of the Ferris wheel, the readings of the weighting scale, which is n, is equal to your actual weight plus the centripetal force plus mv squared over r. So it will give you a reading that is heavier than your actual weight. Okay, so if you want to get a smaller value, okay, if now you gain weight, okay, you feel sad, what you can do, you take a weighting scale, you go to Ferris wheel, and then you take the readings when you're at the top of the weighting of the Ferris wheel. Okay, then you can get a smaller reading. So it might make you feel better. So n equals to mg minus mv squared over r. Okay, so which position? At the top. Okay, at the top. The second thing, how to determine the maximum speed. So now you have gone to you're inside the Ferris wheel, and this Ferris wheel is gone crazy. The speed keep increasing. So what is the maximum speed at which the Ferris wheel can be rotated before human flew off the Ferris wheel? Okay, so now this Ferris wheels, okay, it's rotating at a very fast, very high speed. So what is the maximum speed before the human flew away from the Ferris wheel? So how are we going to do? Now you try to imagine again. If you flew off the Ferris wheels, okay, what is the variables? Which variable is changing? Which variable is changing? If you flew off, do you still have weight? Of course you have. The variable that is changing is the normal force. Why? Because you are no longer in contact with the Ferris wheel. You flew off already. You're not sitting, you're not standing on the Ferris wheel anymore. So in this case, we assume n equals to 0. Therefore, from here, you can then calculate the value. Okay, you can then calculate the speed by using W equals to mv squared over r. So V maximum is equals to 1. So this is how you determine. Okay, this is how you calculate it. So by assuming n equals to 0. So once you flew off, you are no longer touching the surface. Therefore, no normal force anymore. All right. So this is how you determine the maximum speed, the minimum speed. Okay, we try to look at the variables at different positions. So when it comes to vertical circular motions, there are more questions that can be asked, right? So the last one, okay, this is what I told you, the examples of conical pendulum. Okay, so examples of conical pendulums, either they use an aeroplane or they use a pendulum, okay, like what I'm showing right now. So if you have a pendulum like this, okay, what are you going to do? You look at the free body diagram. So you have a T pointing towards the wall, okay, and then you have a W going down. But when you swing this conical pendulum, this circular motion is actually happening on the X component, okay, X component. So there's no circular motions along the Y component, all right, no circular motions along Y component. So what we have right now, okay, so this is my T, and then so I have angles. Okay, my angle is at the wrong position. Okay, I don't want here. So angle is here. Okay, my angle is here. So now I'm transferring this diagram into free body diagram. So what am I doing now? Okay, I have an object. This object comes with weight. And then I have a tension. And then this is my angle. Okay, this is my angle. And then what I have, if you look at the diagram, okay, this circular motion is actually along the X plane only, X component. Therefore, my AC is going to just a going to the right along the x-axis. Okay, along the x-axis. So what are you going to do? Now you have a tension that is lying in between x and y component. Therefore, you need to resolve it. Okay, that's why if you look at my free body diagram given here, I have a t sine theta and also t cos theta because I resolve it into ty and tx. Okay, but ty is t sine theta, tx is t cos theta. Okay, so from here, what am I going to do? I'm going to form two equations, one for the x component and one for the y component. So if you look at the diagram, my AC is lying along the x component. Therefore, for x component, I have FC equals to mv squared over r, or MAC, okay, or MAC. So the only force that I have along the x component is just a Tx equals to T cos theta. Therefore, T cos theta equals to mv squared over r. Now, for y component, okay, there's no circular motions along y component, okay, because like I showed you in the diagram, okay, I have only x component. So for y component, Fc is equal to 0. You use first law, okay, because circular motions only occurs along x component. Then you look at the diagram. So according to my diagram, I have two forces along y component, which is a Ty and also W. Okay, therefore, T sine theta minus mg equals to 0 and T sine theta equals to mg. So basically, the idea is exactly same as chapter 4. Okay, it's exactly same as chapter 4. All right. So I think that's it. Okay, so this is the flight. So when it comes to the questions involve flight or involve a conical pendulum, this is a very important equation. Okay, this is a very important equation. So make sure you know. Tangent theta is equals to sine theta over cos theta. Okay, this one you're going to use it very often when it comes to angles, when it comes to vector. Alright, so ini yang biasanya pelajar terlupa. Okay, so that marks the ends of chapter 6. Okay, so that is the ends of 1 hour. So these questions, I will just do a free body diagram with you. Okay, then you complete the rest. Okay, you complete the rest. Right, so kita tak ada masa. So saya akan guna extra sikit lah masa. So if you want to leave the class, you may leave. If you want to continue, then you can stay. Alright, I will still show you how to do it. Okay, I will still show you how to do it. And then if you think 1 hour is enough, if you want to leave the class, you may leave. Alright, ini cuma extra punya. Okay, extra punya. Okay, so free body diagram. Now, conical pendulum I showed you just now. So you look at the positions of the ball. Okay, the examples that I give you just now. Okay, the conical pendulum is on the left-hand side. Therefore, I have a diagram like this. Okay, I have a tension that is going towards northeast. If your object is to the left, then this is how you sketch a free body diagram. Your tension is now going to northwest. Okay, so you look at the positions of the ball. So this ball is on the right-hand side. Therefore, this is how you do it. So angles given, if angles given is the angles between the vertical axis and the pendulum, then when you transfer into free body diagram, then this is where it is. Okay, so vertical component punya angle, vertical component punya angle. Okay, now these questions sometimes very tricky. What happens here is questions they like to give you the length. Okay, it gives you the length and then it gives you the radius. Okay, it gives you the radius. But then it doesn't give you the angle. So you yourself have to know how to calculate angle from the diagram given. Okay, kerap sekali kering berlaku soalan bagi kamu length of the string and then bagi kamu radius. But they are not giving you the angle. Then you yourself have to know how to calculate it. So it forms a right angle triangle. Okay, so now you have a triangle like this. This is your L, this is your R. So angle is unknown. Okay, angle is unknown. So you have hypotenuse, you have opposite. So how are you going to determine the angles? You use sine theta. Okay, sine theta equals to opposite, which is R over L. So from here, you determine the angle. So it often happens in the exam, okay, in the questions, where it gives you the length, it gives you the radius, but without angle. Then you yourself have to know how to determine the angle. So here it gives you the equations, Fc equals to mv squared over r. Okay, this is for the x component. Okay, for x component. So for y component, it tells you summations f equals to 0. Why summations f equals to 0? Because there's no motions along y component. Our circular motion, as you can see in the diagram, it just happens in the x plane. Okay, it just happened in the x plane. Okay, now let's look at the second questions. What are we going to do now? So this is our object. So as usual, we have a x component, we have a y component. So what am I going to do now? I'm going to sketch a free body diagram. So this is my object. Okay. So object, I have two strings. Okay, I have two strings, but it doesn't tell me about the length. Okay, it doesn't tell me about the length. So what I have here, I have a T1, and then I have a T2. Okay, I have T1 and I have T2. Now, if you look at the diagram, where is my circular motion? Again, circular motion is happening on the x component. Okay, it's happening on the x component. So in which it means, if your object is located at the right-hand side, AC is going to the left. Okay, this is my AC. Okay, which is lying on the x component. So for x component, I have FC equals to mv squared over r. So what I have right here, remember, you need to resolve it. Okay, so what are you going to do here? You will have T1x and also T2x. Okay, so let's assume this is my theta 1, this is my theta 2. Now, if both of them, they have the same angle and they have the same length of the string, then T1 will be equals to T2. Okay, kalau dia bagi kamu string yang sama panjang, angle yang sama, so tensions di string 1 dengan tension di string 2 dia sama. Right? So this one, what are you going to do? Okay, now, one force is missing. So this ball is an object, so it has a weight. Okay, it has a weight, W. So now you have T1, T2, and W. So what is going to happen right now? I want to calculate the FC. So this is my AC. So AC is going to the right. So I have a T1x plus T2x equals to mv squared over r. So T1 cos theta 1 plus T2 cos theta 2 equals to mv squared over r. Whereas for the y component, okay, summations Fy again is equal to 0 because there's no centripetal accelerations along the vertical component. Okay, tak ada vertical punya. Therefore, we have summations Fy equals to 0. So what happens here? Now you can resolve it. So if you resolve it, what is going to happen? Now you have, you have T1y going upwards, and then T2y going down. Okay, and the bottoms you also have a W. Therefore, this equation is now becomes T1y minus T2y minus W equals to 0. Therefore, what you have, T1 sine theta 1 minus T2 sine theta 2 minus W equals to 0. Okay, minus W equals to 0. So that is how you solve it. So you look at X component, you look at Y component. Okay, so examples that I show you now when involve a car is a roundabout. Okay, but not just roundabout. Sometimes when you just move around a curve, okay, not a complete circle, but just a small curve. So when the object is at the curve here, okay, when the car is at the curve here, what is happening? It also experiences frictional force towards the center. Okay, so what happens right now? Let's say I'm assuming this is just a curve. So this is my object. Okay, so I'm going to refer to the original diagram lah. I'm going to assume now my object is already in the curve. So what am I going to do here? I have a center of the circle right here, somewhere, okay, somewhere here. So this is my object. Okay, so what am I going to do? I'm going to draw a free body diagram for my object. So it has a frictional force pointing towards the center. This is the center. So this is a frictional force. Okay, this is a frictional force. So of course, if you want to draw a free body diagram from front view, okay, kalau kamu nak draw dari front view, So let's say front view. Kalau kata now you're looking at the object from here. Okay, you're looking at the object from here. So what you have here is now an object with a weight and also a normal force. So if I'm standing right here, the frictional force is going to the left-hand side. So this is my frictional force. Okay, this is my frictional force. And again, if you remember what I told you, AC is always pointing towards the center. So this is AC. Okay, so AC is also going here. So this is how it looks like, the free body diagram, provided if you're looking at it from the front of the car, okay, from the front view. So now what am I going to do? Again, I form equation. Fc equals to mv squared over r. Now the force that keeps my object to move around this curve is a frictional force. Therefore, F equals to mv squared over r. Whereas for the y component, summations Fy equals to 0. So vertical component, I have normal and W. So n minus W equals to 0. N equals to W. Okay, n equals to W. So this is when it involves an object moving around the curve. Right. So the horizontal circle, which I explained it to you just now as well. So let's say now your object is on the right-hand side. Okay, so this is your object. Tension is on its left. Okay, because the string is now on the left-hand side of the object. So this is your tension. And because it's moving in the circle, according to my diagram, my AC is going to the left. Therefore, this is the directions of AC. Right? So Fc equals to mv squared over r. The only force that keeps my object to move in the horizontal circle is tension. So tension equals to mv squared over r. Then how about y component? Okay, so you have just a weight. So basically, it's just a W. Okay, W is equal to nothing. Okay, so maybe it has another lift force, but usually this one, we don't look at the y component. So for the vertical, okay, for the vertical circle, when the object is at the top, now you have to look at the positions of the object. Okay, this is very important. This question, it shows you the car is inside the circle. If your car is inside the circle, first thing that it has is a W. The second thing it has is the normal force, which is pointing towards the center. Why? Because now it's touching the surface here. Okay, and we know that normal force is always perpendicular to the surface. So N and W, they are pointing towards the same direction. Now, what if you have a circular, if you have a roller coaster, but then the car is moving outside? Now, if the car is outside the circle, then the free body diagram would be different. W is still going down, but now because your object is outside the circle, normal force is going up. So you need to be extra careful with the positions of the object, whether it is inside the circle or it is outside the circle. Okay, it will give you a different answer. So when the object is at the top, okay, in the diagrams given, I have N and W both going down. When it is at the bottom, W is still going down, but now my N is going up. Okay, my N is going up. So when it is at the top, the directions of AC is going down. When it is at the bottom, the directions of AC is now going up. So from here, you then determine the equations. So at the top, okay, let's look at the top. So at the top, Fc is equal to mv squared. Now, N and W, they are pointing towards same direction. Therefore, you plus it. So according to the diagram given, when it is at the bottom, N is going up, W is going down. AC is going up, which indicate that N is a positive vector. So W is a negative vector, therefore minus W. So N minus W equals to mv squared over r, for it is at the bottom. Okay, so N is maximum at the bottom. Why? Because when you arrange the equations, you plus the mg. N is a minimum at the top because it minus mg. Of course, different positions, you might have a different N max and N min. Depends on where is your object. Okay, depends on where is your object. If it is outside the circle, then it might be different, right? So the vertical circle, this is the examples I showed you just now. So provided you are sitting inside the Ferris wheel, so what happened? So at the top, okay, at the top, your normal force is going up and then your weight is going down. And then AC is going down. When you're at the bottom, okay, weight is still going down, N is still going up. But now the difference is AC. AC is going up, right? So when you form equations, okay, so FC, this is at the top. FC is equals to mv squared over R. So at the top, your AC is going down. So AC going down, what does it mean? It means downward is a positive direction, upward is a negative. Okay. So what am I going to do here? When it is at the top, I use W minus N equals to mv squared over R. When it is at the bottom, okay, I have N minus W. Okay, still FC equals to mv squared over R. So equals to mv squared over R. This is when the object is at the bottom. Okay, so at the top and at the bottom, they look similar. They have similar free body diagram, but the way you form equation is different. Why? Because of the directions of centripetal acceleration. Okay, so now how about N? So like I told you just now, how to tell which one will give you a smaller reading on the weighting scale, which one give you a larger readings. So N is so according to these equations, N is minimum when it is at the top. Okay, at top. Why? Because N equals to W minus mv squared over R. So at the bottom, N is a maximum. Why? Because it is equals to W plus mv squared over R. So remember, N is the readings on weighting scale. Right? W is fixed. As long as you're standing on the earth, then you have a fixed value of W. Weight, it won't change. The only things that change is the N. Vertical circle, again, this one we explained it just now. Okay, so you have a tension when it is at the bottom. So this is your object. Tension is going up, and then W going down. AC going up. Okay, so when you're at the top, W going down, tension's also going down. Okay, so this is your object. Okay, so W and T, both of them, they are going down. So when it is at the top, okay, so let's recall, FC equals to mv squared over R at the top. Both of them, they are pointing downwards, and AC also pointing downwards. So means both of them, they are positive vector. So T plus W equals to mv squared over R. So when it is at the bottom, okay, AC going up represents T is a positive vector. So FC equals to mv squared over R. T minus W equals to mv squared over R. All right. So at the top, what happens to the tension? So tension is minimum. Okay, so you have a mv squared over R minus W. Okay, when it is at the bottom, you have a maximum tension. So T max equals to mv squared over R plus W. Okay, mv squared over R plus W. So a vertical circle. So this one, I give the answer already. So you have a tensions T1 and T2 because now you don't know the tensions. So you have also an angle 1 and angle 2. Okay, you should have a theta 1, theta 2. So just add the theta 1, theta 2 in the equations. So you are not sure whether you have the same angles or not. It depends on the length of the strings. So at the top, you have a T1, W, and T2. They are pointing, all three of them, they are pointing downwards. When it's at the bottom, T1 and T2, they are going up. W is going down. So from here, you can form equation based on the free body diagram. And remember the very important things, the directions of the centripetal acceleration. So when it is at the top, AC is going down. Therefore, you can just add them up. When it is at the bottom, your AC is going up. Okay, therefore you use T1 cos theta 1 plus T2 cos theta 2 minus W. Okay, because now W is acting as a negative vector. Right? So for both positions, at the top and at the bottom, total Fx is equal to 0. Therefore, what we have along the x component is T1 sine theta 1 equals to T2 sine theta 2. Okay, So done. Okay, so we are done discussing 8 different types of examples here, and that marks the end of today's class. All right. So do you have any questions? No. So if no questions, okay, if no questions, that's all for today.